You need to put the recording, I think, right?
Yes. So, well, good morning in United States, and well, kind of good evening in India, right? Okay, certainly good afternoon in India, and well, I'm very pleased to introduce to you my very dear friend Jim Breakall, whom I have known for upwards of 30 years now. Okay, at Penn State. Uh, Jim had Jim is what you would call a tinkerer. He is always into doing things of different kinds, and that became evident when, as an undergraduate student, he started participating in ham radio and radio antennas and whatnot. Okay, so he got his bachelor's degree from Penn State, and then he went to Case Western, where he got his PhD. And then for a short while, he was also involved he's a faculty member at Naval Postgraduate School in Monterey, California. And he participated extensively. Some of you will know of a code called NEC code for electromagnetics, which he was one of the code developers of. And in fact, the GUE for that code is entirely due to him. Okay. Well, after some years, he joined Penn State, I think in 88 or so.
89. And
89,
I was at Lawrence Livermore Lab.
Lawrence Livermore before that.
A naval school.
Yeah, he joined here, and where he has been. If you were in antennas, you would know his name very well, because the Radio Club of America recently gave him the status of a modern pioneer of electromagnetics, in particular antennas, okay, communications and antennas. So he became involved with the Arecibo National Observatory a long time ago, and takes a very active role first of all, he took a very active role in the design of various antennas for it, and now in the maintenance of it. Okay, so he's going to tell you about what is involved in radio astronomy, how does electrical engineering play a seminal role in that, and I've asked him to make his talk informal, so please interrupt him if you wish to. Okay, ask him a question. He's very happy to take questions. So, Jim, all yours.
Okay, thank you so much, Akhilesh, and I appreciate that great introduction, and welcome to everybody. This is quite an interesting presentation on Zoom all across the world here. It's not something I do every day, and even though we have many Zoom presentations and so forth, but this is really something very great, I think, that Akhilesh is trying to arrange different speakers. And what I would like to do today is give a little bit of history of myself, how I got involved with this facility called Arecibo. Arecibo is if you don't know about it, it is one of the engineering wonders of the world. I would say it was a 1,000-foot dish antenna on the island of Puerto Rico. And I'm going to go through the history of how it got started, why it got started, and also how I got involved in it. I got involved as a student, just like yourselves, but I understand that everybody here are graduate students going for their doctorates. I started as an undergraduate student, as a summer student when I first went to this facility. And as Akhilesh said, I've always been involved and interested in antennas and radio engineering, mainly through ham radio, which is called amateur radio. And I've talked to many friends in India on ham radio as well. But anyway, when you go to a place such as Arecibo, it was the world's largest antenna, basically. And so I couldn't go any other place and have an antenna this big. So it was really wonderful. Anyway, as Ockley said, I've been at Penn State since 1989 as a professor in electrical engineering. Okay. Okay, let me make sure we're. So this is Puerto Rico is shown from a satellite. Puerto Rico is in the Caribbean and Atlantic Ocean, pretty near the equator at about 18 degrees north. And if you look very, very carefully here, you can see the 1,000 foot, which is 305 meter dish. Okay. And I wonder, can anybody see it yet? Just curious.
No.
Well, turns out right here, I don't know if you can see my pointer. There's a,
Yes, we can see your point.
yeah, there's a
Yes,
little dot right there. Okay, that is the 1,000. So that's pretty amazing. This whole island is 100 miles. I'd have to do the conversion to kilometers. Probably Aklish can do it faster.
160.
Okay, and it's 30 miles this way. Okay, so it's 100 by 30, and this is 300 meters, and it still shows up on the satellite. Here's a little bit closer in, and so now you can see this dish 1,000 feet, and we call it the eye into the universe because it one of the purposes is to use it for radio astronomy, where you look at all the objects in the universe, but not in invisible light, but in the radio spectrum. And we'll talk a little bit about that. It also is unique in that it's also a radar. And so there are very powerful transmitters at this facility, and they can send signals out and bounce off of asteroids and planets and things like that. It also can be used as a radar to probe the atmosphere above the Earth, called the ionosphere. And so that's another purpose. Another thing to notice is look at this topography here. Very, very up and down. Okay, it's actually called karst topography. And the reason is all these holes in the land are sinkholes. It's mainly limestone. So there's hills and valleys, and it's very, very rugged and irregular. And so when the thing was the first thoughts of putting an antenna so big on ground like this, this was perfect ground to try to find a hole big enough that could fit such a large antenna. You may have heard also, I don't know how many people are familiar with Arecibo, but unfortunately, Arecibo in December of 2020 collapsed. And it was a very, very sad day for many people. And you'll see why, because it's been in existence for some 50 to 60 years. And so when it collapsed, that was a sad day. But we'll talk about that in a little bit. Okay, so why was Arecibo first thought of? It turns out back in the late 1950s, some of you may have heard of a thing that happened. The Russians launched something called Sputnik, and so there was a satellite, and so there was a lot of interest in the atmosphere and radio waves interacting with the ionosphere and so forth. And so the military was very, very interested in our government after the Sputnik launch in 1957. And so this one professor knew of a technique called incoherent scattering of radio waves in the ionosphere. And basically the radio waves are such a frequency that they just travel straight up into the ionosphere, but they don't get reflected back. Normally at lower frequencies, like where you have the normal AM radio stations, if you know frequency, it's around a megahertz. And then in the shortwave frequencies, 3 to 30 megahertz, the radio waves can get bent, and basically, you think of them being reflected off the ionosphere, and that's how you can have radio waves travel long distances at those frequencies. But if you go high enough in frequency, the radio waves pretty much go straight through. They don't get bent back to Earth. But there is a small amount of scattering that occurs from the electrons and ions that are in the ionosphere. And so if you could build a radar and measure this scattering, you could then determine things like the density of those electrons in the atmosphere and their distribution on height, temperatures, things like that can all come out of the physics. So the ionosphere is a plasma, basically. And so if you could basically work by studying the ionosphere, you're really working in a big plasma laboratory in the sky. And so this professor, William Gordon, who was a professor at Cornell University, came up with the idea to build this great big radar. And his idea, of course, when you think of antennas or even optics, like a telescope, you would think of having a parabolic dish, okay, or a parabolic reflector. And so the first idea was to put a parabolic reflector on the Earth and feed the dish with an antenna feed and put power into it and send the beam straight up. And so that would be it. You would just send the beam straight up and get the radar scattering back. Well, anyway, this is that karst topography. You can see that this was the original, the way it looked in the beginning, and it sort of has a round shape, but it doesn't really look like a dish too much yet. In fact, here's what it looked like. It was actually a tobacco farm that it started out as, but it was bowl shaped. And so this was picked to be the location to put this huge antenna. So this is the person, Professor Bill Gordon, Cornell University, one of our premier universities in the US. And you can see some drawings here and parabolic dish and so forth. But then some people got a hold of Professor Gordon, and they said, yes, that's a very intriguing idea to put a radar and then use this incoherent scatter theory, and we can measure the ionosphere, but it only is going to be able to be aimed straight up. And other areas of science, such as astronomy and maybe sending radar beams to other planets and asteroids, it's not going to happen unless they just happen to be in the main beam, because it's a fixed beam from the Earth. So work was being done at other locations, and the military and the government knew about some of this other research on what are called spherical reflectors, not a parabolic. A parabolic reflector, as you may know from a mirror that you've seen in optics, has one focal point. And so if you can take the sun's rays and have a parabolic dish and put something in the focal point like a piece of paper, it will start on fire. It's one focal point. But a spherical reflector, we'll show later, does not have a single focal point. It has a line of focus, but since it's a sphere, it has spherical symmetry. And so the antenna can be moved and the beam will move. And so now that's a way to move the beam, and the radio astronomers could study other objects in the sky. The radar beam can be moved to other locations like planets and other objects. And so that was a tremendous suggestion to not use a parabolic dish, which would have been very, just not much science could be done with that. But to have a spherical reflector, then a lot of science. And it turns out there is a limit how far you can move the antenna, because you run out of the dish. If you keep moving to the side, eventually the sphere, because it's a truncated sphere, you're going to run out of the dish, and so the energy is going to go less as you move to the side. But Arecibo could get pretty much good performance from straight up, which is called zenith, out to plus or minus 20 degrees. So there was a 40-degree angular sector that could be covered, and then of course all the way around in azimuth. And so the original cost from the Advanced Research Agency of the government and the Air Force, military, who funded the Arecibo Observatory, was about 9.7 million back in 1960 dollars, which would be about 87 million dollars in today's dollars. But we will see, to replace Arecibo, because I mentioned it collapsed in December of 2020, it would actually take about 600 million to replace it in today's dollars. So a lot of excavation had to be done to that original sinkhole, limestone sinkhole. You can see the limestone here. And the idea was to put a reflector, spherical reflector in this bowl, and then to have 3 towers. We see one being erected here in 1961, and a big platform would sit above, and then all the antennas would be located in that platform and move in angle from zenith, and also all the way around in what's called azimuth. Okay, this tower is about 400 feet tall, which would be about 120 meters or so, to give you an idea of the size. And remember, the dish is going to be 1,000 feet or 305 meters. So that was 1961, here's 1962. And if you look closely, you see that tower, and now another tower, and then another tower is going to go up over here. And you can see more excavation, and buildings are starting to appear here, and so forth. So as I mentioned, up in the center, and you probably could see if you're looking at me here, you see the completed thing in my background. But down at the bottom of that sinkhole, this is the beginnings of the platform. And the platform would hold a big long arm that we'll see later that's called the azimuth arm, and there'll be a big ring around this, and all the antennas can move up and down the arm and rotate around. And that's how they could steer the antenna beam of what's called a radio telescope. Well, here's the platform, and now the 3 towers, there's the base of one of the towers here. The 3 towers are up, and they have cables between the towers and winches, and they start raising this platform up in the air. And the platform goes up to about 500 feet above the bottom of the dish, or I guess that's about 150 meters or so above the bottom of the dish, or the sinkhole here. It's not a dish yet. So there's the platform held up by these cables, and then eventually more and more cables will be added because this thing is going to have the big arm coming up and a lot of other structure, and it's going to get very heavy. And so there'll be huge bridge cables that will go between the towers to hold this up. You can also see that now there's a lot of cables that are going down from the rim of what's going to be the dish. And there's actually some panels, or it's actually like a mesh. Okay, it started out as a mesh, and you can see some of the mesh that's going to form the metallic reflecting surface. So this is the construction of that big arm, as I mentioned. The antennas will be fastened with little buildings to the bottom of this arm here, and they will be able to be moved plus or minus 20 degrees from straight up. And then this arm will be attached to a ring. Here's just one little section of a ring, and that will allow this whole structure to rotate around the ring. Did somebody have a question? I thought I heard something.
No, there was no question.
Okay, fine. If you do have any questions, please speak up. Okay, here you can see now the platform. It's really getting finalized. You can see the ring completely finished. And now the arm is being, this arm is being lifted up. And this arm will be attached to the ring. There's motors here, and this whole thing can rotate around the ring. And then you'll see little buildings here where the receivers and other things are located for the radio astronomy and the radar. And then these buildings can move up and down this arm. And so you can see when the building is right here, the beam goes straight up. When the building is out here, the beam goes up at an angle, and it's at a 20 degree angle. And this picture was taken from down below, and you can see how far up this structure is. And again, the dish would be down here in the sinkhole. So there has to be a way for the people to get out to this structure, and so what's called a catwalk was formed. It's just a long walkway that would go out to the structure, and this is the beginnings of the catwalk. Also, there has to be a way to get the signals from down below and from transmitters. Remember, it's a radar, and there's a lot of power involved. Up to 2.5 million watts of power is in the radar system. And so to transport that power, it's transported over what's known as a waveguide. It's just like a big tube that the energy goes through, and at microwaves. And so the waveguide was also put along this top of this catwalk. And these people here, I would say, are pretty brave. I don't even see any I hope they have some safety cables, but it doesn't even look like it. Looks like they're just standing out there. And so it's you have to be pretty brave to do something like that. Well, then here's the catwalk completed. And so this is how you can walk out and get there. You still have to be pretty brave to walk out here as well. And then you'll notice on top here is this track. That is where the waveguide is eventually installed. And the waveguide would send the transmitter power for the radar out to these little buildings, and then antennas are going to be hung from these buildings. And remember, I said if it was a parabolic dish, we could just put an antenna right here, but because it's a spherical dish, there's going to be a line. And at the frequency of the radar, which is at a frequency of 430 megahertz, the line has to be 100 feet long, or about 30 meters long. And so it's quite a big antenna. Okay, well, here's putting the surface on the main reflector, which is 305 meters in diameter. And this is like a mesh. If you think of, it's actually sort of called chicken wire. It's what they normally would keep the chickens in a pen or something. It has little openings, sort of like the screen of a window, in fact, but the openings are maybe about an inch opening. And that allows the Arecibo reflector to have very good reflection of radio waves up to about 600 megahertz, okay? And so when it first started, it could reflect waves up to 600 megahertz. And later I'll mention that there was an upgrade to much higher frequencies. But you can imagine these people hanging on all these cables and installing this mesh, and it has to conform to a spherical surface. There they are again, just hanging out here. And I don't see any safety cables much, so I don't know. I guess the safety agencies were not there in 1963 like they are now. And you'll also notice there's quite a distance to the ground below. That's done intentionally with there are a lot of cement blocks that pull down the dish, because the dish has to have this spherical surface. And so that's why you see in some areas a lot of height. Also, the holes let the sun's rays go through, and that keeps the vegetation growing, so there's no erosion of the surface, or else the dish would start moving. There you can see a lot of the surface, and you can see straight right through it. So the sun's and the water, of course, has to get through to keep the plant life growing underneath, so there's no erosion. And you can see some areas where they haven't put the surface on yet. Okay, here's one of the first antennas. Remember I said it's not a single point where the focus is on the spherical dish, it's along a line. And so what this is what's known as a waveguide again. It's just a sort of like a hollow pipe, and radio waves can travel in this pipe with very little attenuation. But then there's all little slots along here, little holes that will leak out energy. And the energy comes out in a very, very structured manner with certain amplitudes and what's called phases or time delays. And so everything from all the rays that would reflect off the dish from some distant object, by the time all the rays hit each of these holes and then combines back to this region, they all are combined in focus, just like a parabolic dish would do. But it's a very clever thing that then allows the feed to be moved, and you can still collect all the rays, and that moves the beam of the antenna. So here's just some ray tracing, a line feed. If you think of rays, basically, if the rays are coming in, okay, each of these rays would come in basically parallel, from a distant point, and then they reflect off the surface. And of course, the angle of reflection and the angle of incidence are equal. And then all these rays go along here, and here's a blow up. And so the rays will cross over along this line. So if we could put an antenna from this point down here, we could then collect all those rays, but they're coming in at different time delays. And so that's why the antenna has to have all those slots and different shapes to get this all back in focus again, where we can collect it up here at the feed point of that line feed. And then you can see if you just move the line feed, you then can move the beam from straight up to this direction. And so that was very clever and really saved Arecibo for many, many years for being a premier research facility, especially for the radio astronomers. Well, this is on top of one of those very tall towers, and you can see the size. There's many of these cables that hold up the platform, and you can see the size of things here. And so it's saying the last pin, this is being positioned down here, and then they put a pin in here and a big bolt like this and tighten it. And there's many of these cables that it's basically like holding up a bridge, okay? And very, very huge. So in 1963, the facility was completed, and now all of the mesh is on. The diameter is 305 meters. The platform is supported by all these cables, and the azimuth arm can rotate around the ring, and the antennas, these line feeds shown here, attached to little buildings, can move up and down. And the waveguide goes out along this catwalk from the building below where the transmitter is located. And these are the offices and all the equipment for receivers and so forth that radio astronomy needs, and radar astronomy. And of course, there was a big dedication in 1963. Again, the military did fund it, but it turns out the military pulled out very quickly, and the facility was open to be a international facility where any scientist could go there and do research. It was eventually taken over by what we call in the US the National Science Foundation, NSF, and that's a premier research funder of many, many different fields of science, National Science Foundation. So then in 1972 to 74, they decided that the dish did not go high enough in frequency. There's a lot of radio astronomy that they would like to have observations much higher than 600 megahertz and go up into the gigahertz. And so they decided to replace all that, what we call chicken wire mesh surface, with aluminum panels. And you can see all the panels being stored here that will replace all of that mesh. There's 38,000 of these panels. And I should say 1974 was a monumental year for myself, because that was the year that I went to Arecibo as a summer student. I applied to the National Science Foundation and was selected as the first summer student from Penn State University to go there. There was about 12 students from all around the world, actually, from different universities. And we went there for the summer and had different projects. And I first got to know what research was like. And I was only an undergraduate student in my third year of the 4-year, what we call our bachelor degree. And it was a monumental opening of my life to see how research is done and meet scientists and many famous people, and it really got me interested that I want to do the same thing. I want to be a researcher and work in science. So that's something. When you travel to some of these research facilities, you never know where it's going to lead you in life. Well, here's the last panel. And these panels look like they're solid, but they actually have little tiny holes, pretty much the same as like a microwave oven has little holes in it. And again, that's to let the water through and the sunlight go through. But the frequency of the radio waves, it can go up to 12 gigahertz and it still is a reflector. Frequencies above 12 gigahertz, then they don't get reflected anymore. But that allowed the observatory to observe at much higher frequencies and to build radars at much higher frequencies. So that's the last panel going in. And you may recall that I showed that waveguide. That was a square waveguide that had all those holes in it. Well, that worked okay, but it wasn't very efficient. It only had about 25% efficiency, which means that the energy, 25% of the energy was lost and it wasn't going to the dish. And so this very ingenious person, pioneer in antenna, reflector antennas, Alan Love, came up with a new line feed. And this was it here. Again, it was also about 100 feet, about 30 some meters long. But it was much more clever in that it had slots that went all the way around, and it was tapered, and it could do a lot of more amazing things, and it achieved an efficiency of some 70%. This other person here was one of the directors of Arecibo. His name is Frank Drake. And Frank Drake also was a very famous radio astronomer from Cornell University. And he was the one that started something called SETI, which was the search for extraterrestrial intelligence. And he was a famous astronomer at Arecibo. And when I became a professor, of course, I mentioned that I was a summer student there as an undergraduate. And then later I did my graduate work there and did my PhD research at Arecibo. And that opened up a tremendous world of things. And then I became a professor, as Professor Lataki mentioned. And then I took my students to Arecibo, and this is one of my graduate students that I took some years ago. And we're sitting in front of the big radar console, 2.5 million watts of power at 430 megahertz that studies the ionosphere, as I said, from the incoherent scatter. And I was joking. I said, "Don't hit this button here. That's the button that if you have an emergency, you shut down the whole radar." And so here's the replacement of the mesh with the panels, just to show you what it looks like. It really looks like a solid surface when you put those panels on, but they do have little holes in. So with this upgrade of the surface, the new surface basically conformed to a spherical surface. Remember, the surface diameter, the whole reflector is 305 meters in diameter, but it had an RMS error of less than 3 millimeters over that whole surface. And that was done by installing little reflecting mirrors on each panel and using a photo system with lasers and so forth to basically get the surface and then instruct the maintenance people to go and turn screws on each of the panels so that they could move them up and down. And that whole process of the calibration of the surface took about a year. They also, I'll mention this later, this was a big thing I was involved in. They actually involved lower frequency operation, and then, I'm sorry, high frequency operation. And they could go up to much higher frequencies to observe things in the universe that were of importance to astronomy. And also a new radar was put in, a 1 million watt radar at what's called S-band for doing what's called planetary radar and asteroid radar to look at planets and asteroids. And in 1974, when I was there, a professor and his student started research on what's known as a binary pulsar. A pulsar is a star that rotates and it sends out a radio wave, much like a lighthouse. And then a binary pulsar is two of these pulsars rotating. And he recorded the orbits of these pulsars for many, many years, up to the 1990s. And he was able to, they were able to show that the change in the orbit was from the loss of energy into what are known as gravitational waves, which was predicted by Albert Einstein in his theories. And for this work, they got the Nobel Prize in physics in 1993. So anyway, the areas of operation, radio astronomy was about 70%. Planetary studies, as I said, the radar to look at planets, asteroids, comets, 15, and about 15 for studying the atmosphere. And in its heyday, these were the number of employees and investigators, 300 investigators per year from other places coming in. 100 institutions used Arecibo. Here is Professor Joe Taylor from Princeton, and his graduate student was Russ Holtz. And you can see how they plotted the change in that binary pulsar. And this change was the result of the general theory of relativity of Einstein and gravitational waves. And you may have heard of something today called LIGO that also has detected gravitational waves. And so when LIGO detected them, then all this past history came out again about Joe Taylor detecting them at Arecibo. And I'm going to talk about Joe Taylor. He's quite a close friend of mine, and I'll talk about some things we've done further. So,
Joe,
yes,
Jim,
go ahead.
May I just interrupt you and just to point out
certainly,
to everyone
please.
here that what you have just shown is a remarkable convergence of not only electromagnetics, but also astronomy and physics. Okay. And there must have been undoubtedly a lot of material science needed to come up with these various structures.
Yes,
So,
yes, certainly the mirrors that or the reflectors that I'm going to talk about. Certainly, there had to be a lot of material science to make sure those things would not move, and the materials that were used, in the actual dish and the towers and all that. Yeah, certainly. So anyway, there's, as I said, atmospheric sciences is mainly this feed here. And then I'm going to talk, there was another upgrade we're going to talk about, and this big dome was built. And this dome basically allowed to have normal type antennas, like horn antennas, and antennas that would normally feed a parabolic dish from a point could be inside this dome and then feed the dish. And I'll talk about that. and we didn't need these line feeds anymore. Okay, and there's radar astronomy. Radar astronomy, of course, is a transmitter. It sends a very, very powerful wave, bounces off the dish, and has a tremendous beam, much like a laser beam, if you're familiar with a light pointer, that goes up, it goes right through the atmosphere at these high frequencies, and then can reflect off an asteroid, and you get an echo back. Here's an asteroid here. This was all done. It looks like it was done from an optical telescope, but this whole movie was done with radio waves. And so it's all because of Arecibo having such a narrow beam from this huge reflector. They could get the resolution to show these asteroids that are rotating. And so it's not optical, and that is not an artistic rendition. That is actually from the radar imaging of that asteroid system. Okay, so I mentioned another upgrade came, and this was in 93 to 97, and it's called a Gregorian. There are different types of telescopes, optical telescopes, that have multiple mirrors or multiple lenses. And there's one that's called a Cassegrain, and then there's Gregorian. And so a Gregorian has two mirrors, and then the main primary mirror, which is the 305 meter. And if these mirrors have the correct shape, they can basically bring all the rays to a single point, much like a parabolic dish. And then you can use standard antennas that we can obtain, and it makes life so much easier to work with. There was also a big screen that was put around the whole dish to get rid of interference from noise that the ground has, and interfering signals. There was new motors put in. All these line feeds were replaced with this Gregorian, with new antennas, new receivers that are at very low temperature to reduce noise. There was a new transmitter for the radar that gave twice the power, and the surface was calibrated again, and now the observatory could work with signals up to 12 gigahertz, which is extremely high. That's way up in the microwave region. Here's this big reflecting screen. This is about 60 feet high, or about 20 meters. And this went around the whole dish. And this was to basically to keep out interference, and to shield the ground. The ground is at a very warm temperature, but the antenna is at a very cold temperature called the sky noise, and that it sees. And so you don't want to have the antennas looking at the ground. And temperature is very important because that allows you to see much weaker signals. Here's the Gregorian system. This was a reflector. It had to be this shape. And then here's another reflector. And basically the rays that are coming from the main dish bounce off this reflector called the secondary. Then they bounce into the tertiary, and they come together at a single point here. So if you could put a standard antenna at this point, then you would have a perfect illumination and focusing of the whole system. And so this system had to be protected from the weather. And so it's in this dome called the Gregorian dome, and here it's being raised up, and it's going to be fastened to the arm. And this whole structure here weighed about 300 tons, okay? And with this dome and everything that's in there, that added another 600 tons. And so the total structure with the dome is 900 tons. And so there had to be many more cables that had to be installed on the platform to hold this extra weight. And it was really a a monumental engineering achievement to have this up there. And then this dome would move up and down this arm and then rotate. Inside the dome now, standard antennas could be put in there, and they were put on a rotating floor inside the dome. And so if they wanted to go to some frequency, they would just rotate the floor to that focal point. And then these are all the receivers above the antenna. The antennas are down below the floor, and I'll show a picture of that. And then these are the receivers. But it turns out in radio astronomy, it's not just the receivers, it's electronics, it's a refrigeration system. And so it's mainly the refrigeration is more important because you have to cool the receivers down to very, very low temperatures. We're talking tens of degrees Kelvin and so forth. So they get the temperature very, very low. And so all the electronics are in these big refrigerated cryogenic cooling systems. This is just what the dome looks like. It's basically a 3-story building. There's the secondary, the tertiary, and you see the stairways and here's the bottom of the floor. And there's many antennas that are here, and this floor rotates, and these are the focal points right here. Here's a close-up of the antennas, and I actually designed some of these antennas myself from Penn State, and they are used for radio astronomy and so forth. But these antennas are very easy to build in a way, and they're not those long line feeds. These antennas can cover more frequency ranges, and so this was a tremendous increase in performance to go to the Gregorian system. There's more antenna. I designed this antenna back here. And here's my students again, looking out of the Gregorian dome. There's that big long line feed that was for the incoherent scatter. They kept that there, of course. And here's the bottom of the Gregorian. So all the rays from the dish would go through this hole and then go into the secondary mirror and the tertiary mirror and then to the focal point. You can see the arm here and how things can move up and down and rotate around. And on that arm, there's stairways, and there's my students walking down. There they are there standing along the arm. And then the Gregorian dome is fastened to that right below here. And then, as I mentioned, there's these huge cables that are supporting the platform, and they have to be anchored. And so these are anchors, and the cement goes way, way down into the ground here to hold the platform. There's a car, you get an idea of the size. Okay, here's the catwalk from the platform as the students are getting on it. And here's the waveguide here. Remember I mentioned the waveguide is this pipe that sends the energy from down below in the building at 2.5 million watts. And then it travels up the waveguide, goes around, and eventually gets into that big line feed system or into the Gregorian. The Gregorian, it could go in there as well. So here it is, 1998, that was all finished, the Gregorian dome. And also they decided to add a museum up here. And this was the visitor center. And they eventually got about 100,000 people a year that would come and visit. And there was a museum. And they got all the schools over Puerto Rico would send the students in all grades to come to the observatory on a field trip. That was a big day for the schools. Okay, a system that I got heavily involved in design was a way to use very low frequencies, not up in the microwaves and where the radio astronomers, but very low frequencies with big antennas to illuminate the dish with a lot of power. 600 kilowatts of power, And what this does is this heats the ionosphere or modifies the ionosphere. Remember I said the ionosphere is a big plasma. And so this is like a plasma laboratory in the sky. And if you can modify the plasma, you can do all kinds of neat science and even create reflectors. And you can create what happens in the auroral region. It's called Aurora Borealis, the northern lights. And you can create your own northern lights in the equatorial region just by modifying the ionosphere. And so there was an array of antennas down here that we built. And then there had to be another reflector. And this system is called a Cassegrain system. So you only need one reflector here, Cassegrain reflector. And the energy from this array goes up, bounces off this, bounces to the 1,000-foot dish and goes up in the sky. But it's a much lower frequency at 5 and 8 megahertz. And before, you may remember, we were at 430 megahertz and 2.3 gigahertz and 12 gigahertz. This is much lower frequency. There's a picture of the antennas. They're called dipole antennas, and an array of them. And effectively, because of the effective gain of that big reflector, we get megawatts of power, hundreds of megawatts effectively from the transmitters. And that's enough power that you can modify that plasma. And then the plasma physicists can do a lot of different experiments in the ionosphere.
Excuse me, sir.
Yes, a question.
Yes, sir. As we know, the plasma is the any state of the matter. Can we modify or it convert into other state? As you said that this can go to the ionosphere in which the plasma state is. So we
Yeah,
have to modify.
I didn't hear very well. Maybe Aklish, did you hear the question better? Okay, now you're better. Say the question again.
Yes, sir. Yes, sir. My question is that can we convert the plasma state into the other state? As we know that we can convert the solid into liquid and liquid into gas.
Oh, I see.
Like-
Convert the state of matter. I don't think there's enough energy to do that. And remember the temperature, they're very high temperatures. There's also the plasma is moving. There's tremendous winds that are blowing the plasma. And so there's a lot of a Doppler and temperature effects. I don't think we have enough energy to change that, but we do change the state of it. There's no question. And we cause irregularities. It's called plasma irregularities. And we can change the temperature and things like that. But I don't think we can change the complete state of it go from plasma to something else. But that would certainly be interesting if I understood your question.
Jim, Jim, what you have said is correct, of course, but you're talking about the plasma in the atmosphere. But we routinely change gases into plasmas inside, say, thin film laboratories.
Right.
Yes, but that's in a confined volume, of course.
That's right. That's right.
Does that answer your question, Shweta?
Yes, sir. Okay, thank you, sir.
Yeah.
Another question is, can we ask?
Oh, yes, certainly. Please do.
Yes. Sir, I can see I see the mass of the reflector in the presentation. I want to ask that what the type of the material is used in the mass of the reflector. It is a thin sheet of any material or a metal type or other substances.
Oh, yes, yes. Those panels are made out of aluminum. And each panel is about 3 feet by 6 feet. and they're made out of aluminum, but they have little tiny holes in them so that the water and the light can get through. But the radio waves at up to 12 gigahertz reflect. And so, but they are all made out of aluminum. And then they're supported by many steel cables underneath. And then there are tie downs where there's cables that pull each panel down to cement blocks that are on the ground.
Okay, sir. Can this mesh of reflector reflect only the radio waves?
It's mainly the radio waves. It doesn't reflect certainly anything will reflect at any frequency, but whether it gets any kind of enhancement or focusing, it will create a focus beam of optical, for instance. It's just that's way too high in frequency. So it's mainly for radio waves, and every radio wave will reflect and up to about 12 gigahertz. Now, clearly, if you go lower in frequency, then the wavelengths get very big, and so as you keep going lower in frequency, it's not going to form a beam as well.
Okay, sir.
Okay.
Actually,
Any other questions?
yes, sir. I want one question. Means, sir, this can only reflect the radio waves. Means other electromagnetic waves can be absorbed by this
Or transmitted.
or transmitted. Yes,
Yes, they do. Yes.
Yes.
So the heating of this can be occur. Means so the heating will be occur. The mesh in the mesh of the reflector.
Certainly now one of the reasons of putting this in Puerto Rico was that the temperature variation all year is only 6 degrees, and so but during the day there's a diurnal variation of temperature from cold to hot, and so the whole platform will expand. I mean, the dish and the platform will expand and move, and so they have these cables that pull down on the platform and with motors on them in what's called a feedback system, and so they can keep the level of the platform and the dish pretty much constant by this feedback. But yes, with temperature effects will certainly affect the system, because this system has such a high accuracy, 3 millimeters of surface accuracy, that any movement could upset the focusing of the radio waves. And so, yes, they do take into account the temperature effects.
Okay, thank you, sir.
Okay, you're certainly welcome. Any other questions before we move here? Okay, I just was showing this is the transmitter facility for that HF system that modifies the ionosphere, the plasma, and there's 6 100 kilowatt transmitters in this building. And I should mention later we're going to see that the whole thing collapsed, but this building is still intact, and the antennas they've been able to put those back up at the bottom, but we need to put that mesh, the reflecting mesh has to go back up, and so that has to be constructed again. And so the first thing that may get resurrected from the collapse is this system right here. Anyway, this is the Casa grain mesh that you saw hanging, but before it's put up, it looks like this, and I actually call it the mess, okay, because it is a tremendous mess of wires and things crisscrossing and so forth. But when it does get up, it looks like this. And so here's the antennas down at the bottom, and each one of these antennas has 100 kilowatts of power. That goes up to this reflector that reflects it to the main dish, and then the energy goes up. And so there's the shape of this. And then depending on the frequency, this thing can be raised up and down too to give some focusing. Now, Arecibo has also been in the movies. Okay, I don't know if you've seen these movies in India over the years, but one was a James Bond movie called GoldenEye. Another one was Contact. Contact was actually a book and a series on our public broadcasting here in the US by a professor named Carl Sagan. Carl Sagan was a very, very famous astronomer from Cornell University. And he was a very, very good speaker to the public about astronomy and science and the universe. And this movie, Contact, was from a book that he wrote. And this is Pierce Brosnan. He's a famous actor in the James Bond movies. This is Jodie, or I'm sorry, that's not Jodie Foster there. No, this is Jodie Foster. She was another famous actress in the movie Contact. There's what Arecibo looks like lit up at night. That's quite a nice scene to see lit up in the sky in the countryside of Puerto Rico. And we've had some famous visitors, as I said. This was our president, Clinton, came there. There's Pierce Brosnan, James Bond, Jodie Foster, Sheldon Reynolds. He happens to be interested in astronomy, and he was in a famous music group here in the US called Earth, Wind and Fire. And there I am at 21 years of age. Maybe some of you are the same age. Hair a little different, of course. And I was there doing graduate work at Arecibo. This person was a good friend of mine. He was the head of telescope operations. And this person here is the same person, Professor Bill Gordon, who first came up with the whole idea back in late 50s. And so there's Bill Gordon in later years, and we worked together. And then Akhilesh just mentioned ham radio, and I've been involved in ham radio for many years. Well, one thing you can do with Arecibo that's very easy is you can send a signal out of Arecibo and then bounce it off the moon, and then the moon acts as a reflector and it bounces it back to the earth. And then you can communicate with other people by what's called Earth-Moon-Earth path, or moon bounce. And with Arecibo, it's so easy because the antenna is so big that the signals are so strong, and anybody around the world that has a very minor antenna could communicate with us. And so myself and this person here, Angel Vasquez, he's now the current director of telescope operations, and my good friend Joe Taylor, who won the Nobel Prize. We all three got together, and we had several days where the observatory let us have control of the whole system, and we bounced signals off the moon and made communication all around the world on ham radio, which is very rare. It's a very difficult thing to do with normal antennas, but with Arecibo, it's easy. And there's Joe Taylor and myself. We're doing communication off the moon, and we were in the main journal for the ham radio. We wrote a article in there and made it on the front cover. Okay, I mentioned about the collapse of Arecibo. Some of you may have heard about it in the news. The whole thing collapsed. The cables had some defect internal. We don't know exactly, but I'm sure this is where materials research would really come in, and to try to find the cause. And it probably was water was getting in, and the cable started corroding internally. There have been studies by the National Academy of Engineering and so forth, but nobody knows the exact details of what happened. One cable actually broke back in August of 2020, and they were going to try to fix that and study other cables. And then another cable broke, and they determined that this thing was not fixable, that it was too dangerous, and nobody was allowed to be underneath the facility or around the facility. And they had cameras set up because they thought they knew that it was going to come down. They just didn't know when. And there was also drones flying to capture it. So I'm going to show this, and it's pretty terrible to watch if you've been associated with the observatory for many years. But you maybe haven't seen this, but you're going to see the whole platform and the towers break off, and it's all going to fall into the ground. Notice the top of the tower came off, and the other top rolled down the hill there. Okay, this next shot is a drone that's up on top of one of the towers, and you're going to see the cables. You can already see some of the cables have split here. The tower just broke off and rolled down the hill here. And it destroyed about 40% of the surface as well. Anyway, that thing came down. That was, even though people knew that it probably was going to happen, it was a tremendous shock. And for something that had been around so long and had done so much research and so many discoveries in astronomy and radar, and looking for, asteroids that could come hit the Earth and things like that. So the company that cleaned up the attack in New York, called 9/11, the Twin Towers, that same company was hired to clean up what happened at Arecibo. And basically they removed about 40% of the surface. There's just the dirt there now. They removed all the things that collapsed. And so now Arecibo and the whole community of scientists and engineers, everybody is trying to figure out how do we replace it or come up with something better. And so it's going to take years before some of that happens. But that one facility that I designed, the HF facility that can modify the ionosphere, we think we can get that up faster. And so we're hoping that we can still do something there. But anyway, some of the cost to replace Arecibo, if we just rebuilt the whole thing, pretty much the same, they estimate it would be about $600 million. And the National Science Foundation doesn't have that kind of money just sitting around. And so there have been people that have gone to our government to try to get the money, but it just hasn't happened yet. And so there's still a lot of lobbying and discussion and ideas, maybe a bigger dish. Some of you may, if you're very into the astronomy, you may have heard of another facility similar to Arecibo called FAST, F-A-S-T, and it's built in China, and it's actually a 500-meter dish. So Arecibo used to say we were the largest reflector in the world, but now China can say that. But the China system only is for receiving signals. It's only for radio astronomy. It doesn't have a radar or transmitters. And they've been having some problems with FAST as well. It looks like they're not getting much above about 1.5 gigahertz, but it is a pretty tremendous facility. You could look it up sometime, FAST. It's in the southwestern part of China. And those people from China actually did visit Arecibo some years ago. I was there at the time, and I actually talked to some of those people, and they asked a lot of questions about how we constructed it and things like that. There's ideas of maybe not having one big single dish, but having an array of many smaller dishes, like a lot of radio astronomy facilities have done. And so we're not really sure what is going to happen next. But there still is a lot of the system intact with that HF low frequency facility. So I think we may be able to get that going with maybe a few $1 million, something like that. There's also optical facilities there. There's something instead of radar, where it's the radio waves, it's called LIDAR. And LIDAR is where you have a laser beam that goes up into the atmosphere, and it also scatters optically. And by looking at the reflected scattering of optical energy, the photons, you can basically determine similar things in the atmosphere of densities and winds and temperatures and things like that. So that facility is still intact. And so that's still there. And they did have another very small dish, only 12 meters, but they can do some astronomy with that, waiting for Arecibo to come up. Another idea, and I don't have a picture of it, unfortunately, I should have put that in there, is if you've ever seen a modern sports stadium, they'll have a camera that's supported on cables, and they can move the camera around the field. It's called a Skycam, TV Skycam. And we've been talking to that company that makes the Skycam, and they use it extensively on our football games here in the US. And in fact, Penn State, even at their stadium, has this Skycam system. And we think we could put an antenna up there, and instead of having that big platform, just have a receiver and an antenna, and we can move it around with the Skycam, and it would have enough accuracy that we think we could use it for radio astronomy. So that's just another idea that we've been thinking of. So anyway, that's pretty much it for the discussion. As I said, you never know where life is going to lead you. You may go on be a summer student someplace at some facility, and you get so excited and you meet so many people, and then you find out that leads the rest of your life. And that's what's happened to me. I started at Arecibo as a student and being interested in antennas before that with ham radio. And I've ended up, my whole life working with antennas and radios and teaching and things like that. And I basically dedicate, and Arecibo is responsible for that, is my feeling. So thank you, and I'll be glad to answer any further questions. I hope you found this presentation enlightening and of interest. Thank you.
Sir, I am curious to know about that. Can we use this Arecibo technology for in the depth of the sea for searching missing submarines and ships? Like,
I didn't quite follow the
She's
question.
asking if we can use the technology underlying Arecibo for desktop reception.
Oh, for what reception? For
like searching missing submarines and ships in the depth of the sea.
oh, okay. You're talking about searching for extraterrestrial intelligence.
Yes,
Yes. Arecibo had something called SETI online, and it would use every person's computer that wanted to volunteer. And so they would, Arecibo would provide the spectrum of radio waves. And then there would be many channels that would have to be looked at to see, is there anything that could look like, say, a signal from some extraterrestrial ET. and so yes, there were many, I guess, thousands and maybe millions of people that got involved in that program. And that was a very famous program to monitor and see if they could filter and find out. So far as I know, they never found anything yet. but and actually, when Arecibo for many years, that kind of thing was actually frowned upon. That was not permitted to use the facility to try to search for extraterrestrials, because there's a lot of scientists that study probability and statistics and know all the stars in the universe, that say it's very difficult that we will ever have contact with any extraterrestrials, if they are out there, which I think they probably are. But anyway, then the SETI program became very popular, mainly with that movie Contact. The person that Jodie Foster was trying to represent was Jill Tarter. Jill Tarter is a very famous person in the SETI program, and Frank Drake. And so the SETI became very popular, and also they had money. They were starting to get a lot of money. And so Arecibo needed the funding as well. And so Arecibo was used for that. And that SETI online, where desktops were used, became very popular. Of course, now the observatory has collapsed, so we need to bring it back to continue that SETI research. Yeah. Of course, SETI has other telescopes that they use as well.
Jim, do you think we should be sending out signals to extraterrestrials about our existence? They may think that we are worth a snack.
Yeah. Well, as you know, we've been sending out signals for years and years, ever since radio waves were transmitters. And so some of the things that the extraterrestrials might see from these TV shows, they're going to not have any interest in us, I believe. But then there are other things. But yeah, the thing with Arecibo is, remember, when you study radio astronomy, you're looking at stars that are emitting radio waves. They emit all kinds of spectrum. They emit ultraviolet, infrared, optical, and radio waves. And so when you look at a star with a radio telescope, you're seeing the radio waves emitted. If some extraterrestrial many light years away is looking in our solar system, okay, they'll see our sun, obviously. But if Arecibo was turned on and they were looking at the beam coming from Arecibo, it would blind them, okay? It's much, much more powerful than any radio waves that come from our sun. So Carl Sagan and others did send out a message, and it was a famous message that was sent many years ago, and who knows if they have the methods of detecting and decoding, but clearly anybody looking at our Earth and Arecibo's turned on, they would definitely see it. So the question of whether we should be doing this, I don't see any harm in it myself. I think it's good to be looking. I think it would be the most amazing thing in my life if we actually had some proof that there was life out there, even on some life on our solar system. I think would be such a monumental, breathtaking discovery. So I wish it would happen in my lifetime. I don't know if it's going to. I don't think it's going to, but you never know. So, but yeah, I believe it's out there. It's just the universe is too big, and there's too many planets. Arecibo was the first place that a planet outside of our solar system was discovered.
Yeah,
And
Alexander Wolfshan discovered it, right?
yeah, Alex
Yeah.
Wolfshan, who is a professor now at Penn State in astronomy. He was a scientist at Arecibo, used Arecibo to discover that. He's from Poland, and he got a stamp for the letter for his face on it for Polish stamp, which is pretty neat. But anyway, yeah, he discovered it. Now there's many planets and many.
Now I think it's more than 300.
Yes, and many Earth-like planets are out there in solar systems. So it just, to me, it's like easy to think that it's obvious that there has to be other life out there. I mean, when you look at all the variations of life on the Earth and look way deep in the ocean, and life can exist in high temperatures and all kind of things. To me, there has to be life in the universe out there. And I think it would be really change our whole philosophy and history of the Earth moving forward if we find it. What is your feeling, Akhilesh?
Well, I certainly think there is more intelligence beyond us, and part of the proof of that is that most humans are so low intelligence themselves.
Exactly.
It can be easily topped up.
Yeah. Now that's the thing. The intelligence could be so high.
Yeah.
That you know, there could be never communication. But in this Frank Drake had an equation. It's called the famous Drake equation, and it looks like how many stars there are, how many solar systems, what is the probability that they became an intelligent life and technologically advanced. And then if they're technologically advanced, of course, he thought like the way humans think. He said they're going to come up with atomic weapons, and then they're going to destroy the whole planet. So it came out that it was a very, very low probability that we will ever have contact with any other civilizations in the universe. But hopefully he's wrong. But
low is not zero.
Yeah, it's not zero. And hopefully all these civilizations don't destroy themselves, and hopefully we will not be one of those. But we've come close, and it seems like these days we sometimes seem like we're coming closer, and it does worry me.
All right, other questions?
Yeah. Hello, sir.
Yes, Subhajit, go ahead, please.
Yes, please.
Yeah. Sir, I want to ask that what are the criteria of finding life beyond Earth? Is it we first have to find some planet just similar to Earth or anything else?
Boy, that's a good question because life is what we know of life. Life in some other place may be completely different. Maybe life exists in super high temperature or some way. I don't know. Clearly, if we think like we think, then we try to look for planets that and solar systems that are like ours, and then we aim our radio wave receivers at those kind of places. And so that's I believe what the SETI. I'll be honest, I've never been involved personally with SETI myself. I guess I believe it's neat to do it, but there, you know, there were times it took a lot of time away from the regular research of the observatory, but I was always for doing it. They used to do it when it started, they would have the main scheduling of the telescope. So astronomy got so much time and radar and so forth. And then if an experiment, something happened, it would always be a backup. So then they would put SETI on, and then the SETI data was then sent to all the computers of regular people that had computers in their homes. And then in the background, they would be crunching the data from SETI to see if there were any strange signals. But yeah, I would think that since life as we know it has to have the, you know, the really unique properties of our planet, such as, you know, the ultraviolet shielding of radiation, and the temperature has to be just perfect, and things like that. Clearly, we would think that maybe life would be similar because of the chemical elements in the universe are very similar throughout. And so I would think you would look for planets that are similar to ours. Makes sense. But I'm not an expert in the SETI work, so I like to build the antennas that they can use to try to find the extraterrestrials.
Other questions or comments? All right, well, let's thank Professor Breakall, and I will stop the recording. Thank you, Jim. Thank you very much.
Oh, well, thank you. And
Thank you.
I'm really very happy to do this, and I'd be happy to do it again sometime if we ever have that opportunity. And I'm always, at being a professor, as Akhilesh knows, this is our life, to try to help younger people advance and get their careers moving, because that's what happened to me. So I'm really happy to give this today and look forward again. And good luck to all of you in whatever fields. I understand you could be in all kind of fields of engineering on this today. And I hope maybe some of you might even get involved in this field of astronomy and radio and antenna engineering and electromagnetics too. So clearly Professor Lataki is also a premier researcher, world expert in those fields as well. So thank you so much, and I appreciate it.
Thank you.
Thank you, sir. Thank you, sir.
Thank you very much, sir.
Okay, bye-bye now.
Bye-bye.
Bye.